So if I translate theorem 5.9, the book's calling the inverse function g, and I'm calling it f inverse. So if I want the derivative of the inverse function at 2, then I don't need to find the inverse function. I can just use this theorem that allows me to evaluate the derivative of f, the function itself, at, I know this is a confusing theorem, f inverse at 2. Okay, so the question is, well, what happens with the input for f inverse, this number 2, the input for f inverse is going to be the output on f, right? That's the relationship between our functions and our inverse. So for example, or to draw it out for you here, I'm trying to find, what I'm going to do is find the output here. Plug in 2 to your inverse function. Right, that's this number here, this whole thing. And then I can evaluate that at the derivative of f. So how do I do that without actually finding the inverse function? Well, we know that the input, when I plug in 2 to the inverse, it'd be the same as if I looked at f and found the input of f. That'll be the output of f inverse. All right, so those two question marks represent the same number. So that is the idea, that this value right here is this value right here. Okay, so that's my hint. If you can use f and figure out what the input is when the output is 2, then that result will go here, and you can take the derivative of f and evaluate it, and that'll give you 1 over that will give you your derivative of the inverse at 2. Okay, so I hope that helps.